Today we're going to talk about how to factor polynomials with four terms by using a method called grouping, and we're going to talk about how to factor the sum and difference of perfect cubes. In this first example, I'm given four terms, and these four terms do not have anything in common. They do not have a common number that can be divided into all of them, and they do not share a common variable. So, in a case like this, I'm going to do factor by grouping. I'm going to look at the first two terms and ask, what do these two terms have in common? Both of these are divisible by 4, and they both have at least a k squared. Once you've established what they have in common, you're going to divide that number into both of these terms and write what is left over in the parentheses. 4k squared divided into 20k cubed is 5k. 4k squared divided into 4k squared is positive 1. Now, whatever sign you see in the middle that splits your groups of 2, I want you to write that down. In this case, it's a plus sign. And then I want you to ask yourself, what do these two terms have in common? They're both divisible by 5. Once I divide each of these terms by 5, I am left with 5k plus 1. Now, we're going to ask one more time, what do these two terms have in common? They both have 5k plus 1. I'm going to leave that 5k plus 1 in parentheses. And then beside that, I'll put a second parentheses. This second parentheses will hold what is left over when I divide 5k plus 1 out of each of these terms. I'm left with 4k squared plus 5. Now, before you circle your final answer, check both of your parentheses to make sure that you have truly factored out everything that they have in common. And as long as each of these binomials is in simplest form, then you are done. In this second example, we do have something in common, a number that can be divided into all four terms. In a case like this, you need to go ahead and divide out this common term. All of these are divisible by 3. Once I do that, I'm left with 15n cubed minus 20n squared minus 6n plus 8. Now, I'm going to look at them two terms at a time. When I look at the first two terms, 15n cubed and negative 20n squared, and ask what do they have in common, they're both divisible by 5n squared. When I divide 5n squared into each of these terms, I am left with 3n minus 4. The middle sign in this case is a negative. I want to write that negative sign down. And then I'm going to ask myself, what do these two terms have in common? They're both divisible by 2. Since I've written down this negative 2, I need to make sure and divide negative 2 into both of these terms. Negative 6n divided by negative 2 is positive 3n, and positive 8 divided by negative 2 is negative 4. Now, I'm going to look at these two terms and ask, what do they have in common? They both have 3n minus 4. When I take 3n minus 4 and divide it into both of them, I am left with 5n squared minus 2. In this final example of factor by grouping, I don't have anything in common, so I'm going to start it the same way I did number 1. I'm going to look at the first two terms. What do they have in common? They have a k squared in common. If I divide k squared out of each term, I'm left with 5k plus 1. I'm going to write down my negative sign and then ask, what do these two terms have in common? They're both divisible by 4. When I divide negative 4 into both of these terms, I'm left with 5k plus 1. What do these two terms have in common? They both have 5k plus 1. When I divide 5k plus 1 into both of these terms, I'm left with k squared minus 4. Now don't stop. The second parentheses is the difference of two perfect squares. If you can do additional factoring, you always should. K squared minus 4 factors into k plus 2 and k minus 2. And now you're done. These next 4 examples that we're going to do all have to do with the sum and difference of cubes. You may or may not know your cubes, but it is a good thing to know maybe the first 5 cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed, 27, 4 cubed is 64, and 5 cubed is 125. These are common cubes that show up in a lot of our problems. When you are calculating the sum or difference of two perfect cubes, you're going to use a formula. In this formula, you're going to have a small parentheses that has a binomial inside of it and a large parentheses with a trinomial. That's going to be true for both the sum and the difference. The first thing that I typically tell my students to do is to determine the signs that will go in each of these parentheses. And we use SOAP to help us remember it. SOAP stands for same, opposite, always positive. Same as what? If I'm doing sum, then I'm going to start with the same sign that I have in my original problem, a plus sign. Then I'm going to write down the opposite sign, and I will end with always positive. In difference, you can see the sign that I will start with is a minus sign. Then I will do the opposite, and I will end with always positive. Now that you have determined your signs, I tell my students to look at each term and take the positive cube root. So the positive cube root of a cubed is a, and the positive cube root of b cubed is b. And these will be what we focus on using throughout our formula. You're going to do the first term and the second term in this first parentheses. Then you're going to square the first term. You're going to multiply the first term times the second term, and then square the second term. You'll notice the difference of two cubes uses these same identical variables, a, b, a squared, a times b, and b squared. So in our example, I want to take the positive cube root of the first term, and I get x. The positive cube root of the second term is 3. These will be the terms that I will use throughout my answer. So I'm going to put down a small parentheses and a large parentheses. I'm going to use SOAP to help me determine the signs. Same, opposite, always positive. Now, to fill in the numbers and variables, I'm going to do the first term and then the second term. I'm going to square the first term. I'm going to multiply the first term times the second term, and then I will square the second term. All right, let's do this one more time. Both 27 and 125 are perfect cubes, and this is the sum. So I'm going to start by finding the positive cube root of each of these terms. The first one is 3x, and the second is 5. I'll put down a small parentheses and then a large parentheses, and I'll use the word SOAP to help me determine the signs. Same, opposite, always positive. To fill it in, I'm going to write down the first term, then I will write down the second term. I'm going to square the first term. I'll multiply the first term times the second term, and I will square the last term. In this example, you might notice that neither one of the numbers are perfect cubes, only the variable is. But these numbers have something in common. They're both divisible by 3. So let's divide a 3 out first, and then see if our numbers are perfect cubes. They are. And this is the difference of two perfect cubes. The cube root of my first term is 1, and the cube root of my second term is 5m. Don't forget, this 3 that we factored out needs to remain at the front of our factors. Let's determine our signs. We're going to start off with the same sign, then we'll do the opposite, and the last one will be always positive. I'm going to put the first term here, the second term here. Now I'll square the first term. I will multiply the first times the second, and I will square the second. Here is one final example where the terms do not appear to be perfect cubes initially, but when we divide out what they have in common, we see that we do have perfect cubes. When I take the cube root of the first term, I just get u, and the cube root of the second is 5. Remember, keep the 2 out front because it is part of the factor. Use SOAP to determine your signs. Same, opposite, always positive. First term, second term. First term squared, first times second, second term squared.